Recordings are all up, and I think all of yours are okay now. There were a couple of them. There's actually two recordings for one of the classes that I they're still corrupted. I went on the original Zooms, but something happened when it converted it over. So I don't know if I'll be able to get them, but all of yours are up. So we're talking about the algorithm itself, pseudocode. So my algorithm called merge sort, which is going to take a first and a last. If you are setting this up um, as static, if you in when you're actually implementing this, you can make it a static and pass the array. You can attach it to the array and make it a member method. You could just use a global array. Actually, for your project, probably a global array would be the best way because you're going to keep a temporary um, sorted array and then the original random array so you can keep reusing the random. So, but whatever you want to do, that's up to you. Like I said, you're adults now. Okay. Now this is going to be the original naive version. So if first is still less than last, we're going to find the middle of the array. And it's an integer, so if it's an odd number, it's just going to truncate it. Okay, and then we're going to recursively call merge sort from first to mid, and then from mid plus one to last. And then I'm going to put naive here or basic. Then we call the merge. And the merge works from first to mid to last. Okay? That's the algorithm. The merge itself is what takes. We'll talk about that. I'll have directions up for that, Stephen. No, I don't want, yeah, the file CPP or Java, the individual files, don't zip it. I just have to unzip it. And with this 45 of you, if we can cut any of the work we can cut, helps. But I'll give you the specs because I don't want, I mean, the submit, submission specs. I don't want somebody sending me like all 10,000 runs. I've had people do that. No. And remember, the main point of this is you're running this so that you can analyze it. Okay? I mean, and that's what I want you to get. We're not running this to show me you can get the code off some website and run it. I know you can do that. I want you to do an analysis of it. So to really show what's going on and why and And to see how practical, see the practical ramifications of running it on hardware versus what we're doing. Okay, so now the idea of this thing, these are the two recursive calls. This is the part that actually sorts. So in effect, what we're doing with merge sort is I'm taking my stack of 100 test papers, and Andy and Anthony each get 50. And you know what? Sort them. Have fun. Give them back to me when you're done. I'll put them together, but give them back to me when you're done. And Andy says, "Look, wait a minute. I'm not doing this. Ayub, Azam, you guys, 25 each. Have fun. Give them back to me when you're done." And Ayub says, "Brandon, Devinda, here, take 12 or 13 papers, sort them, give them back to me when you're done." Okay, so we're passing it along. We're not actually doing anything. We finally get down to the bottom, and Mateo and Owen are standing. They each have one paper. And they look, oh, mine's ahead of yours. They pile them on top of each other and pass them back up. And then it works its way up from there. So by the time it works its way back through all these layers of handing stuff out, I get two piles of 50 papers that are completely sorted. And all I have to do is now intersort. I know the top paper of each pile is the first one, so start there. And just keep intersorting, picking them all up. How long is it going to take me? What would the runtime be to just take those N papers, those two piles? Say I had the two piles of N over two papers. Okay? How long would it take me to just put them back together?
Can I guess?
How much?
Can I guess? Because I don't
Yeah,
really know.
understand.
I'm gonna say all of them.
O of N. I'm picking up one paper from each pile and looking, comparing which one is smaller and putting it down. That's it.
Okay,
Now,
I
when
got
we
it.
look at the actual, I am going to frame out that merge code a little bit. Um, I actually have to pick them up one paper at a time and make a pile and then put that pile back in the original folder or whatever. So there's a little bit of inefficiency with the merging. I need temporary arrays to hold the data, um, which is why merge sort is a little slower than the other divide and conquers. Now, what about the runtime for merge sort itself? What is the runtime? Let me just put here, merge. This is actually its data event. I have to look at every paper at least once, or at least half of the papers at least once. And then I have to put them back into the folder. So that's got to be an order N runtime. What is the runtime for the merge sort algorithm itself? Do I know?
I want to also guess all of them.
Okay, now let's think about it for a second. Merge sort is working by calling merge sort, right? It calls merge sort on the left half of the array, and then it calls it. You know what? I better ask a question here. I mean, I was figuring you've probably been looking at this stuff over the weekend, at least looking. I know some of you had the program running already. Um, people had time for me the other day. But I really didn't expect that. That was a nice surprise. Um, how many of you remember the basic idea of merge sort? Not that you could write it syntactically correct, but so you remember divide by two, right? So I don't actually know what the runtime for T of n is, just looking at this. But what do I know about this recursive call? The runtime for this recursive call.
Isn't it
Merge
log
sort
of
from
n?
first to mid. Huh?
It's a log of n.
Okay, this is going to be a divided by two type thing, right? This is going to be whatever T of n is, the first call is on half of it. So it's n over 2. And this one is also n over 2. And then when it's all done with that, it's going to call this guy. So I don't know at this point exactly what this runtime is, but I can say I can write a recurrence relation. The T of n is, T of n over 2, and then I do another T of n over 2. So that would be 2 T of n over 2. And then I do merge, which is some constant times n. I don't like the way I wrote that dot. We'll put Cn. I'm sorry, everyone got a late start because everyone else in the house is working in the little kids' school system. My daughter-in-law has 3 and 4-year-olds, and my son is elementary and middle school. So, well, my husband retired, but anyway, so nobody had to get up. They're actually able to stay home and play in the snow, although they're not going to play in the snow because it's 60-mile-an-hour winds, but that's okay. So now we're at a point, look at this nice recurrence relation we have. Once I have that recurrence relation, can I use master theorem? I've got T of n is 2t n over 2 plus c times n to the first power, n to the d. And anyone remember, since you were supposed to know it for a quiz today, remember you have to know asymptotics for Wednesday. I figured with the, it wasn't that I didn't figure people would come, although that's what's happening, I guess. I don't know. But I was afraid that if the public schools went remote, we didn't know, until yesterday afternoon that they were actually closing. I was afraid about the systems becoming unstable. Okay, I mean, and let's face it, there's 250,000 people online today on CUNY, so. All right, so our master theorem, it's set up for a T of N is A times T of N over B plus N to the D, right? That was the formula that we used, and we went through that whole, um, what day did I do that? There we go. So we did the whole derivation of the master theorem back in what date was that? February 2nd. Oh, gee, that was the day it was like below zero. Okay. So if I look at this formula, I have A is equal to 2, B is equal to 2, and then D is equal to 1. And what we came up with was if A was greater than B to the D power, T of N was going to be big O N to the log base B of A. That's got to be written bigger. Like, too many little things in there. And again, remember, um, it doesn't it doesn't really matter about the base. The base is going to be depending on how much we divide. Okay? If in this case we're doing base 2. So we can just leave that. If A is less than B to the D, then we said the whole thing becomes just big O of N to the D. So if A is big, nobody cares about the N to the D part. This A of T, A times T, is what takes over. If A is small, the N to the D part takes over. It will be larger. If A is equal to B to the D, then T of N is N to the D log of N. Okay? That's the statement of the master theorem. So in this case, A is 2, B is 2, D equals 1. A is 2. B to the D is also 2. Therefore, T of N is big O of N log N. Now, I also know, since this is a comparison sort, it's big omega of N log N. Which means, what can I say? If it's big O and big omega, it's big theta. Now that's kind of important because it means merge sort in the best case is n log n, in the worst case is n log n. So its behavior is always going to be n log n. There's no real worst case. Um, what style of recursive code is this? Is this pre-order, post-order, or in order? It's pre-order, right? It does recursive call, and then the work. So that's pre-order. It's doing the work after it looks at the recursive calls. Yeah, see, the problem with merge sort is it's post order. Now, that's one of the reasons there's no worst case. But it's also the reason there's no best case, because even if I had my papers already sorted, I don't look at them. I don't look at them. I just start giving them to you guys because I'm too lazy to do it. It's like Huckleberry Finn with the. Did you guys ever read Huckleberry Finn or Tom Sawyer? How many of you read Huckleberry Finn or Tom Sawyer in school? I mean, I think they still do that, those two. I know a lot of things they tell you to read and you don't. You get the Cliff Notes or the Spark Notes or whatever. Yeah, I taught high school, I know. But remember when they were trying to paint the fence? Whoever was, whether it was Tom or Huck, uh, had to paint the fence and he didn't want to do it, so he told all his friends how cool it was to paint the fence, how much fun it is to paint the fence. It was Tom Sawyer that did that. Although that sounds more like Huckleberry. Um, and I don't know, it's the blizzard knocked that out of my head because I know these books well. Um, he gets everyone else to do it because he told them it was fun to do. So merge sort does that. Whether um whether the stuff is done or not, I'm not looking at it. I'm giving it to you guys to do. If it was already sorted, you're still going to do all the same work because none of you are looking at it either. The only people that were actually looking at it, who did I have doing that? Owen and I got to look at the list. Owen and Mateo, they were the two that were doing that. So you're the only two that are ever actually looking at the stuff until we pass it back up. So because it's post order, no really best case. Because the work is done after the divide. We don't pre-process it. The merge itself, now what? That I didn't do at all. Sorry, my notepad turned itself off. There's some settings wrong, and this is a different pen. And there's some setting that's just wrong on it. It picks up every motion. There we go. Okay. Merge. This is the basic idea of merge. Merge creates a large temporary array. At some point, we have two halves that are sorted. And now we want to intersort them. So the basic code for that is I have one pointer starting over, not pointer, one index starting over here, another index starting over here, and I compare them. I'm going to call this left, call this right. And compare. A left to a right. And copy the smaller one in. So which is smaller, 3 or 1? Clearly, 1 is smaller. I hope we all know that. If not, I give up. Okay. So I'm going to copy 1 into this temporary array and move that over. And now I'm going to compare 3 to 5. 3 is smaller. Copy it in. Move that. Compare 4 to 5. 4 is smaller. Copy it. Move that. 5 is smaller. Copy 5. Move it. 6 is smaller. Copy 6. Move it. 8 is smaller. Copy 8. Move it. Oops! What happened? Yeah. I have either an out of bounds error or in some way I hit the end of that half of the array. Okay? So at that point, I'm done with that right side. And I can just copy the rest of this. Oops. And we really, if I were writing the code out, I just don't want to take the time in class. If I were writing all the code out, I would just have a for loop at this point. Copy 9 and 10. Am I done? Well, I'm done with the sorting part, but I still have a problem because I have all this stuff, but it's not in the original array anymore. It's in a temp. So then I have to actually physically recopy to the original array, which now I can write as one big array. This is my array A. Oops, that's 7. Don't make up elements. There we go. So this is why I said to you before, here's the problem with merge sort. One is that it is post order. This is not a great feature. This is a con because I can't tweak it. I can't make it better. The good part is I can't make it worse, but I can't make it better. The big problem is, so that's problem 1. The bigger problem, problem 2, is I'm creating and destroying temp arrays on every call to merge. So when you run this, you are, oh, thank you for the Huckleberry Finn, thank you. When you run this is why merge sort will be slower than quick sort or heap sort or both, whatever you're running. Because it's constantly making a call on the operating system to get memory for a new array, destroying it when we leave. In addition to the recursion, recursion by itself is slowing everything down. But it's good recursion. And you can see that you're actually generating a tree and traversing the tree in a post-order manner, which is kind of cool. Now, those are the bad features. All these temporary arrays. This makes it slow. But we have good features too. And one pro is it's post order. So no data triggers the worst case. I mean, if it's sorted in reverse order, it's going to be a little slower, going to do more comparisons, but it's not affecting the order at all. So nothing's going to trigger worst case behavior. It's going to be n log n no matter what. This is easy to write as parallel. Each time you call merge sort, you just set up you make another division. So I mean in Java you don't really control that. I mean you can, but any of you play with Python? How many of you play around with Python a little? Or a lot, I don't know. Play around with Python.
Does leak code count?
Yeah. If you've played around with it enough to run some stuff. Because when you learn Python, you can set how many processors you want to use. You can write a simple little thing just to run 2 to the n or 2 or n factorial or something. And say you want to run it on 1 processor, 2 processors, 4 processors. Python will let you just tell it to run it in parallel. And it's nice to do if you've already taken 343, or I don't know if you did Amdahl's law in 240, but you mentioned it in 343 at least, that you know that when you start using parallelism, breaking something up and using 2 processors does not make it run twice as fast. And the more you divide, the less gain you get. Because you're only gaining on the merge call and you're adding extra operating system stuff. So the stuff that has to be sequential is still going to be sequential. You're going to spread out those merge calls, but each one of those merge calls still has to run over n elements, whatever n is. Okay, so it's a diminishing returns type thing on improvements, and there's a limit of how much of an improvement you can make for n processors. You take a limit as n goes to infinity, and you can see the best you can do. But this is an easy program to write as a parallel algorithm. If you take parallel algorithms, I think that's 344. Oh no, it's 344 is the hardware aspect of parallel computing. I think it's 715 is the software aspect. Parallel programming and distributed programming. But the idea is when you write things using parallelism, you're not changing the amount of work, you're just dividing it. And at some point, it's not worth dividing. Another good feature of merge sort is it can do external sorting. So if I have something that's too big for my memory, I can just split the data up. I can sort the 2 halves, and then I can just inspect the same way I did on merge, one at a time. Look at what's going on to find the elements I'm searching for. Okay, so I'll have like A to M on one drive and N to Z on another. That's fine. There's no problem doing that with merge sort. I can split things up. I can keep things in external files. and then search the data as I need to. Remember, why do we sort? We sort to be able to search more efficiently. If we never had to search the data, we wouldn't bother sorting it. Like I said, if we were in the classroom when I'm giving back test papers and that, I don't generally sort them the first day I give them back. I sort when it's going to be, oh, I have to find the people that weren't here. The first day I just call out names and give them out. Now, there's one little thing here that I wrote the basic code, right? I wrote for my basic code, if first is less than last. I want to go revisit that for a minute. Do I really have to go down to everybody's holding one paper before I put the stuff together? Like, if you're holding two papers and the person next to you is holding two papers, could you shove them together fast? Would you have to break it up into each of you gives a paper to the person behind you, they put them together and hand them back to you to put them together? What do you think? You think you have to go down to just one paper before you can start putting the stuff back together? No. And this is that second question, that second big question on your project, to run the same program but on smaller arrays, 32, 64, 16, 128. Run it on a bunch of different arrays because this is a tweak, but it does save time. It doesn't change the order. When I say something is a tweak, that's what it means. It's not going to change the order of the runtime. Instead, the conventional wisdom is 32, but that's why you're running this, to see what's faster on your computer. To do something like if last minus first is less than 32. Use insertion sort. Because even though it's n squared, at 32 or 64 or 16, whatever on your computer, it can run that n squared faster than it can do the recursive calls. So instead of going down to 1, you're going to be breaking out of the recursion sooner. You're going to break out of the recursion. And that's the whole bottom of the tree. So if you think of your original tree of having, 128 elements, this is the merge tree. Then it breaks it down to 64 on the left and 64 on the right. And then it breaks that down to 32 on the left. Okay, if I keep going with this until I have just a whole bunch of little ones, I'm adding a whole lot of stuff, right? If I stop it at 32, I stop the recursion here. And all the rest of this is insertion. At that point, it's just going to be one big array. Well, 4 arrays of 32 running insertion. Instead of running all these leaves on the tree and then traversing my way back up through 5 layers. Do you see that? I actually never drew this picture before, but I kind of like the idea of it. I'm not sure it's my drawing, so it's bad. Do you get what I'm saying? Do you see what I mean? Don't be afraid to tell me no, because this would be a nice thing to ask you that would at least be harder to get through on chat. . 17 people answered me, 18 people. 8 people are ignoring me. I'm ignoring myself. So basically, I'm saying I could cut this divide and conquer to just divide the 128 into 264s, divide each 64 into a 32. So I have altogether, I'm only doing the 6 recursive calls here. Then the whole rest of it is just a for loop. A nested for loop, which is going to run faster than all that recursion. And again, this is what you're going to be looking at for your particular computer language operating system. Okay? Because these numbers might be different between C++ and Java. It might be different on, PC, Windows stuff versus Linux versus Apple. And that's why we're doing this. It might be different. I'll probably have to make minor modifications to my program. But I can run my data too, because my computer's, I think, a lot older than any of yours. Mine's 2019, so it's going to be slower than what you guys have. All right, so that is the merge sort story. Let's compare that to quick sort. So the quick sort algorithm is a whole different approach. In the quick sort algorithm, and I'm going to give you an example of why these things are important to know. In the quick sort algorithm, I'm looking at the data right away. Okay, I told you, I think once before when I started teaching at York College, they were big classes. I was teaching Calc 1, which was a requirement for a lot of the majors. And I was teaching probability and statistics, and I was teaching financial calculus. They all were big majors, big classes. Everyone had to take one of those three. So what they did at York, unlike what we do, it's a smaller school. It's only about maybe 6,000 students in it compared to Queens College with 25,000. Um, so what they did at York is they would just set up um, a Calc 1, a probability statistics, a financial calculus, and they would set them up one at like 8 in the morning, one around noon, and one around 6 o'clock at night because they had a lot of night students, teachers, and nurses, or teachers' aides who were now going for bachelor's, or people who were teaching but needed calculus or something for their master's program. They would set up one section at each of those times. And they were all just staff was the teacher. And they opened registration. And depending on how many students registered, um, like right before the day before classes started, you finally found out your classroom because they could be running, 4 or 5 sections of probability at 6 o'clock at night. They just broke up the 300 students who registered into 4 groups of 75 or 5 groups of 60 and gave them a classroom. Now, I did not realize that's what they did. I mean, I knew when I started that my name wasn't on the uh, registration list, but, I was new. And so when I gave my first exam, I'm a first name person. Those of you who've had me before, you know that. I call you, I learn your first names. Um, when I got my first group of papers, I started doing my good old merge sort. I broke the papers up into A to M and N to Z. And at 60, then I'm already down to 30 or maybe I go to the 15, and then I just do them basically insertion sort, like I sort cards in my hand when I'm playing cards. Um, by the time I had gone through the pile, I realized that almost my entire class was letters A to C. I had one or two, well, I think I had a total of maybe 8 people out of the whole class that were in the rest of the alphabet. I had just gotten the beginning part of the alphabet because they took the roster for the 300 students and they just lopped off 60 at a time. They didn't randomize it. So my merge sort idea of having a pile A to M and a pile N to Z did not work too well. I had to pick a different way to break it up. I had to go to something of what similar to what quicksort does. Quicksort basically imitates, it mimics building a binary search tree. Okay, I'm asking a question. I'm not making judgments at all, okay? There's no judgment in here at all. So don't think there is. There isn't. Okay, this is purely. Who here had me for 313? I mean, I know some of you did. Some of you had for 343. I know a lot of names in here. Right, so U5. You see, I'm not looking at names. U5. Do you remember when we did binary search trees and then we did quick sort? I showed you how quicksort builds the same thing that a binary search tree would have built. Do you remember that? You can just put a thumbs up on that one. Because that I always do. Even, even in the summer when we're running fast, I always show the quicksort builds the binary search tree. Thank you, guys. That makes me feel good. Okay. Quicksort, basically the naive code, the basic code does exactly what a BST would do. And actually, I think most of you probably on the midterm or the final had something that was, here's the code to do a BST and then copy it over using an in-order traversal. And hey, look at that. It's sorted the same way Quicksort would. I don't know what came first. I'm going to guess that, the binary search TID came first and then it became Quicksort at some point. What Quicksort does, it uses an element to partition the array. Less than that element, which we call the pivot, is on the left, greater. Oh my goodness, I can't even guess what I was spelling there. It's on the right. And then it recursively. So it starts off by taking an element and saying, all right, you know what, everything less than that go to the left half of the array, everything greater go to the right half. And then I'm going to just keep calling the partitions. So the algorithm itself for quicksort, again, we're going to have a first and a last. So it's going to go into the array and it's going to partition it. And then it's going to recursively call, basically it's recursively calling that partition from first to pivot -1 and from pivot +1 to last. So we're going from, and you notice there's a little difference here. I want you to see a little notice here. After I partition it, I start the recursion and I go from the pivot first to the pivot -1 and then pivot +1 to last. What happened to the pivot element? I mean, on merge sort, I went 0, first to mid and mid +1 to last. So every element's covered there. But here, I'm not talking about the pivot anymore. Why? What this does, the pivot is already in place. Good. It's already in its sorted place. If everything less than it is on the left and everything greater than it is on the right, then it's in the right place. And that's the beauty of how this thing works. Instead of recopying stuff all over the place, that was the problem with merge sort, right? We broke it up, but we had to copy everything. We had to move it out of the array and then move it back. There's no way around that. With quicksort, I'm switching stuff that's on the wrong side, but that's all I'm doing. I don't have to make temporary arrays. I don't have to get new memory. I've got one location for the swaps, that's it. So that's the idea of quicksort. This partition is again going to be theta of n. Because all I do is I compare every element to the pivot element. And if it's already less than it, leave it alone. If it's greater than it, move it to the right. The rest of these, this is not as neat as merge sort. And it's why we have to do some changes, some adjustments. And I know you know this, you did it in 313. I brought it up in your project. I want you to run it with the basic thing that can cause a worst case, and then try some of the improvements. Okay, any questions? We will pick up with this on Wednesday. Wednesday, you're going to have the quiz too. It's just on little o, little omega theta, and basically, for loop, nested for loops, and then squared and cubed, stuff like that. And a master theorem question. Not to do by back recursion, just to be able to do the ABD thing. Okay, so I'm not looking for you to do a back substitution. I'm planning for no more than 15 minutes. Okay, so there's not going to be back substitution. All right? Okay, be careful when you're out. My husband just came in with a cup of coffee for me, and he said there's about 15 or 16 inches outside of my house. And they're saying there's going to be another 3 or 4 inches. So, just be careful if you're shoveling. Lift with your legs. It's heavy. You're going to hurt your back. And if you're driving, watch it. Okay? All right, guys. See you on Wednesday.
Wait,
Bye.
Professor.
Yeah.
For the project, so like the parts that you told us to answer the prompt question, like where you access like how would you like see the difference? Like do we have to type it up or write it as a comment inside the code?
No, I want you to actually explain. It's going to be a
Explain.
document with it.
Okay. Thank
I
you.
mean, you can comment statements so that you know where your clocks are and stuff, but yeah, no, I want that actually as a document.
All right, thank you.
You're welcome.
Bye.
Okay, Stephen, bye.